MOSFET as an amplifier. So maybe in the last class or before that class we've actually applied some sine wave signal, and we could able to see an amplified version of it. So with a gain of I don't know whether it may be 3, 4 or 5. So I don't remember that exact gain. So let me just take one student with me. Okay, who can come with me? Kirtana? Kirtana?
Yes, sir.
Yeah, fine. So let us try to find out what are the requirements to have MOSFET as an amplifier. First, let us try to understand what is an amplifier is. So amplifier, have you heard of amplifier any time? Okay, Kirtana?
Yes, sir.
Where exactly? May not be in the class. So somewhere, okay, in general, have you heard of amplifiers?
Yes, sir.
Where exactly? Where exactly you might have heard of amplifier? uh, maybe when you're gone to a function where they are speaking in a mic. So if it has to be listened by so many people, then you have to have an amplified version of it. So you need to have an amplifier. So amplifier basically means, okay, you need to increase the amplitude of the signal so that it can reach many people. It can reach many people exactly in case of that loudspeaker system. Otherwise, amplifier is one where you will be actually increasing the amplitude of the signal. So it can be the increase of the amplitude of voltage, it can be current, or it can be power. So what we are looking at now, MOSFET as an amplifier. So even though we call it as amplifier, but it is actually, you are actually increasing the voltage level. So you can specifically call it as voltage amplifier. So to be very specific, so it is MOSFET is used as a voltage amplifier. Meaning, if you have an amplifier, so now you have we call it as a two-port network. So two-port network. What I mean is, it will going to have port number 1 at the input, port 2 at the output. So this we call it as a two-port network. Two-port network. Always amplifiers, voltage amplifiers will be two-port networks. One will be input port, other is output port. So you apply the input voltage here. This is a load which can be a resistive load or it can be reactive load. When I say reactive, you can have of course complex load. You can have inductor as well as the resistor, capacitor as well as the resistor. Of course, this is the load, and you have this as amplifier. So this black box, we are supposed to uh, have it using the MOSFET. So if I call it as MOSFET amplifier, MOSFET is a main element in this amplifier which is responsible for increasing the amplitude of the input voltage, which is V in at the input, and at the output you can call it as V out. V out. Let me also specify something over here. So instead of simply writing V in something like this, we write it as small V in and small V out. Kirtana, can you make out? I'm writing it as small V in and small V out. There is a
Yes, sir.
specific reason, okay, why we are writing it as small V and a small V in and small V out. We always call it as small signal amplifiers. See here, this is small signal amplifier. So here, even in case of amplifiers also, we have something like, okay, amplifiers which can amplify large signal, and amplifiers which can amplify small signal. So what we are basically considering MOSFET is as an small signal amplifier. So now I want to use this as an amplifier which will amplify small signals. When I say small signal, the amplitude is in terms of millivolts. So it can be ones of millivolts to hundreds of millivolts. You will not be applying something like, okay, 1 volt to amplify to 100 volt. So this is not the amplification level where this is a large signal amplification. Suppose if you are amplifying, get 10 millivolt to something like, okay, 500 millivolt. You can see there's a, significant improvement in the amplitude from 10 to 500. How much, by how much it has incremented? Okay, Ratana. Suppose if the input is 10 millivolt, if the output is 500 millivolt, how much is amplification level?
50 times.
50 times. So it is increased by 50 times. You can see we are talking in terms of a small amplitude increase to, of course, this is also not very big. It is still a small amplitude, but it is a small signal amplifier. This 1 volt to 100 volt, here this input itself is large signal, and you are amplifying it to still larger amplitude. So what we are basically considering this MOSFET in this particular course AMCD is, we are treating MOSFET as an amplifier that to amplify small signals. Correct?
Yes.
Okay, keeping this in mind, let us move on. Okay, how do we use it as uh, now we know that MOSFET will operate in how many regions?
3 regions.
3 regions. Okay, MOSFET operates in three regions. They are
Cutoff region,
cutoff. Second one,
on,
okay, in on we have got linear and saturation. Correct.
and saturation.
Correct. So these are the
Yes,
three
sir.
different operation. So here we have VGS less than or equal to VTH.
Yes, sir.
Here VGS is greater than VTH, but VDS is less than VDS
VDS sat.
sat. Here VGS is
Greater than VDS sat.
greater than VTH, and VDS is okay, let me say it as greater than VDS sat. Am I correct? These are the regions of operation, and we have uh, two characteristics. One is, what is this?
Transfer carry.
Transfer characteristics, and this is for a given VDS, and we have other one
Output carry.
VDS, and this is ID. We had the output characteristics. Correct?
Yes, sir.
Okay, this is so and so. Now this is transfer characteristics, this is output characteristics. Of course, this is the MOSFET what we have. So what is this? Shall I call it as VTH? Correct?
Yes, sir. Yes, sir.
So far so good. Correct?
Yes, sir.
Okay, now uh, let us write the circuit of MOSFET. Okay, assuming KP as
True.
okay. With these, can somebody say what is the region of operation of this MOSFET? Is a MOSFET on first?
Yes, sir.
Okay, why? How do you say MOSFET is on?
VGS is greater than VTH.
Perfect. Is a MOSFET is in saturation?
Saturation.
Can we verify that?
Yes, sir.
How do we verify?
VDS is greater than VDS sat.
How do you say how much is VDS now? For that, I should find out what is ID. Half Kp W by L VGS minus VTO whole square. Correct? How much is ID? Can somebody say what is ID? Three point or 320 micro, correct?
Yes, sir. 30.
320 micro, no?
Yes, sir.
Okay, this is ID is equal to 320 microampere. Now how much is VDS now? Can I write VDD, or let me write this as VDD and let me write it as VDS plus minus. Can I write KVL expression for this? VDD is
Yes, sir.
equal to, tell me. Suppose if you consider this as current ID, if you name this as resistance RD, how do I write? VDD is equal to
ID into RD plus VDS.
plus VDS. So can I now find out what is VDS? It is
Yes, sir.
1.8 minus 320 micro into 500 ohm. So this into 500 minus 1.8. So it is 1.64 volts. Correct?
Yes, sir.
So MOSFET is in
Yes, sir.
saturation region.
Yes, sir.
Am I correct?
Yes, sir.
Okay. In this graph, shall I locate that point? Carefully
Yes.
observe. This is VGS. Okay, transfer characteristics. VTH is 0.4. Actually, what is VGS now? In this circuit, in this circuit, how much is VGS? 0.8, no?
Yes, sir.
So shall I write 0.8 somewhere here? Correct?
Yes, sir.
Can I extend this line up to this point and then find out this is my ID, which is equal to 320 microampere?
Yes, sir.
Perfect.
Yes.
Okay, now suppose if this is equal to 0.8 volt, does this current is 320 microampere?
Yes, sir.
Correct. How much is
Yes, sir.
VDS now? 1.64. This is
Yes, sir.
1.8. If I say it as 1.64, shall I say this is that point?
Yes, sir.
Now what I'm trying to locate is, I'm trying to locate point A and B, which corresponds to these readings.
Yes, sir.
Correct? Can I relate
Yes,
it?
sir.
Fine. Now this is they are all DC voltages. Am I correct?
Yes, sir.
This is 0.8 DC. This is 1.8 DC. You have a 500 ohm resistance, and you have a what is that? MOSFET.
Yes,
Now
sir.
I want to use this as an amplifier. This as an amplifier, meaning I need to apply small signal now. Correct? Now before I just move on to that, shall I remove this particular battery and then derive it from this 1.8 volt? Can I?
Yes, sir.
How do I do that? Now what I'll do is I want to eliminate this battery, replace it by two resistors. So something like this. All of you write it. I'm writing the same circuit. It is this. You can see now I'm using two more resistors, which will give me, this is R1, R2, RD. This is VDD is equal to 1.8 volt. This is NMOS. Now if I call it as VG, VG should be how much? 0.8 volt. Correct?
Yes, sir.
Okay. Now for this to be 0.8 volt, from VDD is equal to 1.8 volt, what is R1 and R2? What should be this? Because can I write the expression for this particular VG as VDD into R2 by R1 plus R2? Kirtana,
Yes.
do you know this? Do you know how do you got this equation? Okay, let me just ask you in the chat box. How many of you can understand whatever equation I have written for Vg is equal to Vdd into R2 by R1 plus R2. Do you know how do I wrote it? All of you write in the chat box, sir, I know how to write it, or I don't know how you wrote it. Please type in the chat box, I know or I don't know, because this is a starting point. If most of you don't know, then I need to say how do I wrote it. Type in the chat box. So I know, okay, how to know. I don't know, sir. Fine. Okay, fine. No, please don't worry. So even if you don't know, it's fine. Good. You're all coming up with knows and don't knows. That's good. Make it fast so that I can. Okay, fine. Looking at the chat box response, some of you know, of course, some of you don't know. Okay, let us try to find out how do I write this Vg is equal to. So we know that as we discussed in the previous class, so eliminating this particular segment, I'll just eliminate this segment. Can I write it as this? Kirtana, there is some buzzing sound from your side. Where are you?
Yes, sir.
Are you traveling or what?
No, sir. I'm at home.
Then why that sound? Okay, it's fine. You're sitting in a quiet place, no?
Yes, sir.
That's still fine. Okay. Don't move your mic, okay, here and there. Okay, this is Kirtana. Is this fine?
Yes, sir.
Can I write eliminating this RD and MOSFET? I just simply take out this. If I take out this, does only this is left out?
Yes, sir.
Shall I find what is this current I? What is the current I
Yes.
for this? Okay, let me write what is I is equal to. Shall I write I is equal to voltage VDD by total resistance R1 plus R2?
Yes, sir.
Correct? What you are looking at? You are looking at this voltage, which is this voltage VG, voltage drop across resistor R2. So voltage drop across resistor R2, is it not the current? Does the same current flows here? Because there is no other path. This is the only path available. So does the same current flows?
Yes, sir.
When the same current flows, then what is the drop across this resistor R2? Is it not I into R2?
Yes, sir.
Does that I into R2, is it not VG?
Yes, sir.
Now, whenever I simply say VG, it is a voltage at this point with respect to ground.
Yes,
With
sir.
respect to ground. Ground is this point. It is this voltage I into R2. So I will say I into R2 is nothing but VG. Am I correct?
Yes, sir.
So what is the I expression? It is this. So shall I
Yes,
write
sir.
it as VDD into R1 plus R2 into R2? Is it not VG?
Yes, sir.
That's what I wrote here.
Yes, sir.
Got it now?
Yes, sir.
Now, others, now again, put in the chat box. Could able to get it or not? Again, all of you again put in the chat box. Is this fine? Uh, Again, I'm looking at the response of the chat box. Yes, fine. Got it, sir. Good. It's very simple. You are trying to measure what is the voltage drop across R2, which we named it as VG. VG is voltage at the gate with respect to ground, which is nothing but the voltage across R2. Voltage across R2 is nothing but voltage at gate with respect to ground. So let me just put this as ground. Okay, does all of you got it now? I want each one of you to say yes or no. Even if it is no, it's fine. Okay, how many of you are there in the class? Let me just find out how many of you are there. Okay, we have 53 students. In my Moodle account, there are 56 count. I don't know why still it is 52 now. Because 53 minus myself. Okay, let me take the attendance. Okay, took it fine. Okay, Kirtana, you can mute yourself. I'll ask some other student to join me. Okay, who can I ask? Okay. Ayush Kumar. Ayush Kumar. Yeah, you can be with me. Now we have this. Now we know how to got this VG expression, correct?
Yes.
Then because we are using these two resistors R1 R2, the purpose of using this R1 R2 is to eliminate this one more extra power supply, correct? I want to eliminate this. Now not to eliminate that, we need to have the same voltage as this was producing, that is 0.8. So 0.8 should be derived from this VDD using these two resistors. Now you have only one equation. Now what you have is 0.8 is equal to 1.8 R2 by R1 plus R2. You have only one equation, two unknowns, highly impossible to solve it. In such case, assume one of them. Assume one of them. So let me assume R2 is equal to 100 kilo ohm. So let us maybe discuss later, okay, why I'm assuming it as 100 kilo ohm. Why not 100 ohm? So let us discuss that a bit late. So if I assume this as 100 kilo ohm, find out what is R1. Now if you assume R2 as 100k and all these things, so only unknown parameter is R1, so which you can easily find out using the calculator. Again, don't use your mathematical stuff. Just put that what is that, alpha A as it is. It is 0.8 alpha. Okay, alpha equals, and then open the parenthesis. Okay, it is let me open one more parenthesis. 1.8 into 100 exponential 3, close the parenthesis, divide by, open, alpha A, this is R1 plus 100 exponential 3, close the parenthesis, close one more, shift cal. Oh, it is 125 kilo ohms. Can you see now it is 125,000. So R1 is
Yes.
125 kilo ohm. Would all of you get it? I think most of you could able to get it. It's not very difficult. Correct? So now we have a different circuit now as an amplifier. So we have this is 500 ohm. This is battery 1.8 volt. This is 125k. Correct? This is 100k. Who is there with me?
Sir Ayush.
Ayush. Okay. Is this fine, Ayush?
Yes, sir.
Will it give same circuit as this, same effect as this? Correct?
Yes.
Okay. Now I need to apply the input voltage. I need to apply that input voltage because I want to use it as an amplifier. Of course, maybe on that day when we are discussing this as an amplifier, we actually put a capacitor to block the DC and then apply this V in. You can see I'm writing it as small V in. Correct? This is
Yes, sir.
small V in. I will take out the output voltage at this point, V out. There is one more corresponding voltage here. I will call it as capital VD. Let me differentiate what is this capital VD and small V out. Capital VD corresponds to DC voltage at drain with respect to ground. Correct? This, whenever you
Yes, sir.
write capital V, capital D, it is a DC voltage at the drain with respect to ground. What is a small V out? It is an
Output
AC
voltage.
signal. AC signal because they are all small in letter. Small V, small out. Correct? So this is AC small signal. Let me also write AC small signal. because since it is small, we are writing it in small letter. We just think that way. So if it is DC, it's always capital in capital in representation. This is again VDD. VDD is the entire supply voltage. VD is the voltage at drain with respect to ground, because this is not written. The second suffix is not written. Suppose if I say what is this VG? What is this VG now? What is VG?
So VG is 0.8.
No, what how do you define? It's a DC voltage at gate with respect to ground.
Yes, sir.
What is VGS?
So gate voltage at
It is
with respect to
with respect to source.
source.
Now since you have written both G and S, this can be written as VG minus VS. It is voltage at gate with respect to ground, voltage at source with respect to ground. Since source and ground are shorted, so VGS is equal to VG in this particular case. Correct?
Yes, sir.
Okay. Now, so what is the purpose of this capacitor? I'll call it as CC. There is a specific reason, okay, why we call it as CC. Why not okay, C, KCD, CS, so and so. CC stands for coupling capacitor. CC is coupling capacitor. Why the name coupling is because it couples the AC signal from the input to the amplifier. It couples means it allows the AC signal from the source to the amplifier. So it only couples the AC signal, but it blocks the DC. Ayush, do you know what is the reactance offered by a capacitor usually? XC. You write it as 1 over 2 pi FC, no?
Yes, sir.
Am I correct? What is this F here?
It's a frequency.
Frequency. What is this C?
It's a capacitance.
Capacitance of the capacitor. Correct? We say what are the purpose of using this CC is to couple the AC signal, and the second one is to block DC. Okay, AC, let me say AC input signal. This is to block DC input signal. Correct? How do we say it couples the AC signal? How do we say it blocks the DC signal? We know all AC signal will have frequency non-zero. For AC signals, frequency is high. If the frequency is high, then what is the XC for that AC signal?
So some value.
No, will it be more or less? Assume that, okay,
So
let me come to this. Now for DC signal, what is the frequency?
0, sir.
When the frequency is 0, what is XC then?
Infinity.
Infinite, meaning it blocks the DC signal, meaning it won't. This capacitor, assume that you have an input signal, having some DC component in it. Can you see here? This is having some DC. This is 0. This is shifted above. Can you see this is shifted above? So we have different AC signals. This is an AC signal, something like this. This is with respect to time. This is 0. You have some 10 millivolt, so and so, and you have one more signal which is having something like this. This is 0 volt. This is this is with respect to time. Assume that this is 50 millivolt. Can you see? Does this signal have some DC component? Ayush? Now, what do you mean by AC signal is? AC signal is one where the average area of the signal in the positive half is same as equal to the average area in the negative half, meaning its DC content is 0. Its DC content is 0. We call it as a pure AC signal. Pure AC signal. Whereas here, even though there is a AC signal in this, there is a variation, but this is always above 0. I will say this has some DC component because this is shifted above, no?
Yes.
So if you apply such type of signal to this at this side, see here, if I apply this signal to this side, suppose if this is the signal that is applied at the input, what you will get at the output is, you will get, okay, suppose if you remove this and then try to see it over there, suppose if I don't have this, if you put only that capacitor, I will get a pure AC signal. You can see, is it blocking the DC from this to coming from here to here? Hello?
Yes, sir.
So suppose if I remove this, so what I mean to say is, you have a capacitor, assume that you have a resistor also, and you applied a signal which is something like this. Can you see it is always above 0? It's always above 0. It is at this point. Suppose if you measure at this point, it will be perfectly like this. What is the advantage here? What is the change?
It eliminates DC volt.
It eliminates the DC, so this is a pure AC signal. Pure AC signal. That means whatever DC component that is there at the input will be blocked, if at all, if it is there. If there is a pure AC signal at the input, if you have a pure AC signal at the input, at the output you'll get the same thing. No harm. Correct?
Yes, sir.
But if it has got some DC component, it blocks the DC to enter into the other side. Correct?
Yes, sir.
Okay, now why that is so important? So let us try to find out, okay, why it is so important. Because what is the purpose of putting this 100K and 150, 125K? Ayush?
So to get the VG value.
To get a VGA value of 0.8. Correct? Suppose
Yes.
if you don't have this capacitor, assume that this input DC voltage has around 1 volt DC. Suppose assume that this has got a 1 volt DC and you don't have a capacitor. Does this 1 volt combine with this, or will it have an effectively different voltage than 0.8 when you connect this to this? My
It will
point
combine.
is you have designed a resistor. So you have designed a resistor network that, so you did so and so, correct? So this is 125K, this is 100K, now it is 0.8 volt, correct? This is 1.8.
Yes.
Now assume that you have a source which has got some DC component. The moment you connect this to this, this is no more 0.8. Why it is no more 0.8? Because you have some other voltage also coming. Why you maintain this as 0.8? Because you want to use it as an amplifier where you want to have a current of how much? 320 microampere. So does that affected by this input? Assume that you have this input, this is no more 0.8. Suppose if you have a pure AC signal, will it be 0.8?
No, sir.
See, assume that you have a single amplifier. There are different sources. There is source 1, there is source 2, there is source 3. Assume that this source has got a pure AC signal, correct? Assume that this source has got a signal which is negative DC. Assume that this source has got a signal which is positive DC. Getting the point now?
Yes.
Now the point is, you have a single amplifier, but you have 3 different sources, S1, S2, S3. Now you carefully design this to have 0.8 volt, correct? Hello?
Yes.
To get 0.8 you made this 125K and this is 100K. Now to this amplifier, if you connect this pure AC source which is not having any DC component, does this 0.8 change or not?
No, sir, it won't change.
It won't change because the input is pure AC. It is not
Yes.
influencing that 0.8 volt. Correct?
Yes,
Correct?
sir.
Okay, now for this it is, for this connection of this circuit without any capacitor is fine. Now we come to this circuit. What is the effective DC of that second source, S2?
So, sir, negative.
Some negative. What you have here before you connect it? 0.8. Correct?
Yes, sir.
The moment you connect, it is no more 0.8, it is lesser than 0.8. Does your current change here?
Yes, sir.
So that should not happen to me. Meaning whatever negative DC voltage you have should not be get coupled to this. It should be blocked. Coming to this S1 source, does it has got some positive voltage?
Yes, sir.
So this positive voltage will certainly affect this 0.8. Of course, it may become 0.9, it may become 1.2 volts or whatever, depending on the DC voltage. Now, is it affecting that your DC condition there?
Yes,
Hello.
sir.
So,
So the cycle,
come on.
sir, needs only pure AC signals.
Meaning it should not
Like,
affect the DC component. We call it as biasing conditions should not be altered because of the source. Whatever the source is, this whatever design I made it for the amplifier should be independent of the sources. How do I make it independent? Make sure that this DC voltage of different sources is not coupled to this. You put a capacitor, that will solve the purpose. You can achieve the blocking of DC by having a capacitor, which is this called as CC. It is also called as DC blocking capacitor or coupling capacitor. Why it is called as coupling capacitor? Because
it blocks DC voltage.
no coupling. Why the word coupling? Because it couples the AC signal. Is it not?
Yes, sir.
No, it is certainly blocking DC, but it should couple that input signal. No, if the input is not at all reaching, then there is no point in amplification. You cannot amplify at all. First, that signal has to reach here. So, how that will reach? Because the reactance offered by this capacitor for that high frequency signal is less, it certainly reaches this point and then it proceeds. Correct? Hello.
Yes, sir.
What is the role of coupling capacitor now? Two roles.
So it couples the AC voltage
AC
and
signal.
it blocks DC voltage.
It couples
The
the
AC
AC
voltage
signal from input to the amplifier and
and it blocks the DC voltage.
DC voltage of the signal, if at all if it is there. If it is not there, fine. Correct? So
Yes, sir.
the one more purpose is not to alter the biasing conditions of the amplifier. So of course, by blocking the DC from the input, it will not allow to alter. It will keep the biasing conditions stable. Correct?
Yes, sir.
Okay, fine. So now, okay, let me just take this. Of course, if you can understand this concept clearly, then it is very easy to have another 5 minutes only. So don't think that I'll take it beyond 10 o'clock. At 10, what you have? At 10, what you have?
Constitution, sir.
Constitution of India.
CIP.
Okay, fine. Okay, assume that at this point, how much we have? 0.8 volt. At this point, assume that you have a pure sine wave here. Correct? Is it correct, Ayush?
Yes, sir.
R1, R2. Then what will be the shape of the waveform at this point? This is with respect to 0 time. What is the shape of the waveform here? If I say this is 0, shall I say
It was
whatever?
shifted by point.
It is perfect. It is shifted by 0.8 and you have the waveform. Correct? Why it is shifted by
Yes,
0.8? That is the DC voltage at this point. R1, R2. R1, R2 is making it to shift, and this is your input signal. Can you see? Uh, without the input signal, what was the voltage at this point? Was it this 0.8 at VG? Am I
yes, sir.
correct? Now this is, you can see I'm writing it as capital V, capital G. Perfect.
Yes, sir.
So now suppose if you connect this, the AC signal is superimposed on that. Of course, you will not see both the lines. What you will see is, you will see a waveform something like this. So this is time. This is, I will call it now small v capital G. Small v capital G is, it is a small signal with shifted by the gate voltage. So it is AC plus DC. It is small v capital G. If it is capital V, capital G, it is DC. If it is small v, small g, it is AC. 1 second. Please understand all this. Now, is this a AC plus DC? Ayush?
Yes, sir.
Shall I say small v, capital G? Small v,
Yes, sir.
capital G, AC plus DC. How about only this? How about this?
It is capital VG.
Capital VG, only DC. How about this? How about this? See
Sir,
this?
it is
No, it's a pure sine. Then it is small vg. Correct? This
yes,
is
sir.
small vg, doesn't have any DC component. This is only DC. This is AC plus DC. This is how we represent. Small vg is AC signal, capital VG is DC signal, small v, capital G is AC plus DC. Correct? Okay,
Yes, sir.
keep these new things in mind, and then we'll see how do we use this MOSFET as an amplifier, because the entire AMCD revolves around this amplifier. If we can able to get this amplifier in another two classes, then you can comfortably handle any amplifiers, because it's only amplifiers. That is CS, CG, CD, cascode, you name anything, differential amplifier, all are amplifiers. If you can understand CS amplifier perfectly, then you can crack any amplifier. So don't leave this amplifier unless you get it. Even if you take 5 to 6 classes, I don't mind. So if you can get how does this amplifier works, then you can be very perfect in understanding the further topics. Thank you so much.